Welcome back, everybody. In this video, we're going to start chapter 4, which is about probability. So the plan is to talk about why we're talking about probability at all, and then we're going to go over, take a quick overview of the chapter, and then get into section 4.1. So the first thing to do is to talk about why is it we're dealing with probability at all in a statistics course, and the reason for that is this. We've talked about how our subject, statistics, is based on wanting to know something about some population. For example, let's say that we'd like to know the proportion of COD students that are female, let's say. And so due to the difficulty or expense of the task, we would instead take a sample of, let's say, 100 students, find the proportion of females within that group, and from there decide based on that, that probably the proportion of females in the COD population as a whole is pretty similar. Okay, so then let's say that we've taken this sample of 100 COD students and it turns out that 53 are female. So then based on that, we could conclude that 53% of COD students as a whole are female. Okay, so even if our sample is representative, right? Even if our sample is representative of the whole population, the whole population of COD students may or may not be actually 53% female. There's going to be some variation due to chance. In other words, maybe the true population of COD students isn't 53% female. Maybe it just happened to be 53 females in that batch of 100. That idea of chance is why we're studying probability. As another example, take a look at the two dishes on your screen of M&Ms. Let's say that we've got this bowl of M&Ms. You're sitting and snacking while you're watching TV. You don't look in the bowl. You reach in and you come out with this assortment in your hand of M&Ms. Let's say that there are 3 greens. It looks like there are 3 greens there out of all the M&Ms. So maybe 3 out of the 10 M&Ms are green. From there, is it safe to assume that 3 out of 10 M&Ms in the whole bowl will be green? In other words, are the M&Ms in all 30% green? Or did you just happen to get 3 by chance? Okay, that idea of chance is why we're talking about probability in this course, because probability is basically a number that represents chance or how likely or unlikely something is. Okay, the chapter that we're doing has 4 sections in it. So just to kind of go over those. 4.1 in a way is the biggest. Often the beginning section in the chapter is very important because there's a lot of definitions, any kind of new symbols and things are going to be covered in this first section, and it gets more specific from there. So 4.1 talks about the basic concepts of probability and some of the important formulas involved with it. The relationship between probability and odds is also covered here. There's different rules associated with calculating probabilities. 4.2 is about 2 very important rules, the addition and multiplication rules that have to do with calculating the probability of one thing or another occurring and probability of one thing and another occurring, as we'll see. Section 4.3 is basically more different rules, complements and conditional probability. We'll talk about those when we get there, as well as Bayes' theorem. The last thing, 4.4, has to do with counting, and as we'll see, that's not as simple as it sounds. It's not like we're going to be counting on our fingers there. It's more sophisticated types of counting problems that will come in use when we're figuring out certain types of probabilities. But in this video, we're going to just work on the beginning part of learning about the basics of probability. So let's get started with that. So the first piece is some definitions. In working with probabilities, we study events. An event is basically something that happens, the collection of results or outcomes of a procedure. A procedure can also be called an experiment. So the words procedure and experiment here have kind of a special meaning for this. This is not going to be an experiment like you'd have in a chemistry class, or a procedure that you might have in chemistry class, or a medical procedure or anything like that. It's just a process or something that we could do. It could be pulling a card out of a deck of cards, or rolling a die, or surveying a person coming out of a store, or drawing a M&M out of a bowl, okay? It's any kind of thing or task that you could do to which there's some kind of random result. There's a simple event. A simple event is an outcome, that is a result, or an event that cannot be further broken down into simpler components. So contrast that with a compound event. A compound event is a type of event or outcome or occurrence that can be broken down into smaller events. Okay, we'll talk about how that's done after a while. Okay, the sample space is just basically a list of all the possible outcomes of the procedure or event. The sample space consists of all outcomes that cannot be broken down any further. So easiest to understand the definitions here with an example. Let's say that you roll a die, like the 6-face cube that you play Monopoly with, right? Roll a die. The sample space would be the numbers 1, 2, 3, 4, 5, and 6. Those are the possible simple outcomes that you could get. Okay, each element of that sample space is a simple event. An event is a subset of the sample space. The event getting an even number would be a compound event, because that would be the same as saying getting 2 or 4 or 6. Okay, that is a compound event. A simple event is just a single possible outcome. Get a 3. Okay, that's a simple event. Getting an even number, there's 3 possibilities there. You can get a 2 or a 4 or a 6. Rolling a 5, that's a simple event. You can't break that down any further. Okay, as another example, let's say we've got a deck of playing cards and we pick a card. An example of a simple event would be you draw the 4 of clubs. Okay, a compound event would be getting a face card or a 9. Okay, there's I don't know how familiar you are with a deck of cards. You're going to get more familiar. There's 12 face cards and 4 9s, as it turns out. So we can break down that quite a bit. All right. So that takes care of that part. So let's continue. There are a couple of different kinds of probability or different ways of looking at it. The first way that we'll look at it is the relative frequency approximation for probability. And what that is if we conduct or observe a procedure, roll a die 20 times, or pick M&Ms out of a bowl, or survey 30 people in turn coming out of Walmart. Okay, we count the number of times the event A actually occurs. Okay, based on the actual results, P of A, P stands for probability here, okay? P of A, probability of A occurring, is approximated as follows. P of A is the number of times A occurred divided by the total number of times the procedure was repeated. Okay, and that's based on something that actually happened, actually conducting the experiment, drawing the cards out of a deck of cards, whatever it was, is actually done. The classical or theoretical approach, and this one requires equally likely outcomes. If there are n different simple events, and each of those simple events is equally likely, then if event A can occur in exactly S of those ways, then the probability of A occurring is the number of ways that S can, or A can occur, which is S, and that's divided by the number of simple events, which is N. So that is the probability of A, and it's based on the number of ways that A can occur divided by the total number of possible outcomes there are. Okay, it's important to remember that when you're using the classical approach, the outcomes are all equally likely. For example, let's say that you are playing, I don't know, one of those children's games like Candyland that has like a spinner, right? You flick the spinner, it spins around and it stops on a number. Okay, and let's say that we're playing kind of a weird game and the spinner has this for it. The board, okay? All right, so if it has this for the spinner, when you flick that, is it just as likely that you will get 1 or 3? Okay, thinking it through, what's reasonable is that you should get 3 twice as often as you get 1. So here the outcomes are not equally likely, okay? So that's what is meant here when we say outcomes need to be equally likely. The third kind, and the one that we won't deal with all that much, is just subjective probability. As you know, the word subjective basically is just based on an opinion. P of A, the probability of event A, is estimated by using knowledge of the relevant circumstances. So that's a subjective probability. Okay, I'll give an example after a minute. All right, so let's say that we get a paper cup, like from McDonald's or something. You get a paper cup and you toss it 100 times. Okay, and out of that we keep track, and let's say that it lands on its side 93 times, it lands on its lip, that is the mouth side down, 5 times, and then right side up twice. Okay, that would be an example of relative frequency approximation of probability. We're to say, okay, let's say that we keep doing this, the probability that in the future, if we kept doing this, that it lands on its lip is going to be 5 out of 100, or 0.05. That is, we could expect that about 5% of the time, the cup is going to land on its lip. Okay. Suppose that you have 3 kids, assuming this that boys and girls are equally likely. And by the way, for this whole class, all semester, you can assume that boys and girls are equally likely. Okay. Assuming that boys and girls are equally likely, we'd like to know the probability of you having 2 boys and 1 girl. So I've gone ahead and written out the sample space for us. The possibilities range from having all 3 girls, a girl, a boy, and a girl, a girl, and a boy, and all the way down to a girl and 2 boys here at the end. Okay, so there are 8 possibilities here. The ones where there are 2 boys and 1 girl are here, and here, and here. So the probability of getting 2 boys and 1 girl is 3/8. Okay, all those 8 outcomes are equally likely, and so the probability of getting 2 boys and a girl is 3/8. Okay, another way that we have of describing that or indicating the sample space is with a tree diagram. So let me show you how a tree diagram would go. So the first kid could be a boy or a girl. Okay. So after the first kid is born, it's either a boy or a girl, and that's not going to have any bearing on what the second child is. So the second could be either a boy or a girl. And of course, that won't influence how the third kid comes out. And so the third kid could be either a boy or a girl. So this is going to give us a total of 8 possibilities, ranging from all 3 boys to all 3 girls. If you follow the paths through, the first one here is boy, 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 and then the last one is girl, girl, girl. So all 3. So all 8 possibilities shown up here in purple are listed among the entries in this tree. Okay, so that takes care of it. All right, so the next thing that we want to talk about is the idea of the law of large numbers. And what the law of large numbers says is that if we repeat a procedure over and over again, the relative frequency probability of an event tends to approach the actual probability, or the theoretical or classical probability. Okay, so to illustrate that, suppose that we toss a coin, and throughout this class, you can assume, unless you're told otherwise, that coins are fair in that they're equally likely to come up heads or tails when you toss a coin throughout this whole class. Okay, so the probability of getting tails when you toss a coin is going to be a half. If you toss a coin twice, is it going to necessarily come out heads once and tails once? Not necessarily, right? You could happen to get heads twice or tails twice, right? And there's a probability associated with that. We can figure it out if you'd like. So let's say that we've done this experiment of tossing this coin several times. If we toss the coin 50 times, it's conceivable, we should get about half, right? Half heads, half tails, but it's conceivable that we would get 20 heads and 30 tails. Okay, so there, 40% of the tosses came up heads. Okay, continuing onward, let's say that we toss the coin 1,000 times. Okay, and then number of heads, let's say, come out 497, number of tails 503. So here the ratio of heads to tails is more likely 1 to 1 than it was in the first place. As we increase the number of trials, the ratio of heads to tails is going to get closer to 1 to 1. That is, the fraction of tosses coming up tails will get nearer and nearer to 1/2 the more times we toss the coin. And that is the law of large numbers. Okay, so the relative frequency probability is based on actually performing the task, the experiment, whatever it was. And as you know, there's some individual variation if you do a task a low number of times. But if you do this experiment or procedure over and over again, the relative frequency probability will get closer and closer to the theoretical probability. Okay. All right, our next topic, sorry, in this first section, there's a lot of kind of what seemingly disjointed topics, a lot of definitions to begin with. Okay, so bear with me. The next topic is the idea of the complement of an event. So if we have an event A, and in statistics or probability, frequently we use capital letters like A's, B's, and C's to denote an event. If A is an event, the complement of an event, and that's denoted in several ways, is all the outcomes in which the event A does not occur. There are several ways this can be written. Our textbook uses a horizontal bar on top, A with a bar across it. Other books, or if you're on Google or YouTube or something, they might use a C, a little superscript C for complement, or maybe an apostrophe, a little tick mark up there. Okay, all of those can mean complement, and they refer to the event A not happening. So as an example, suppose that you roll the die, that Monopoly die you had, and if E is the event of rolling a 4, the complement of E with a little bar on top, would be the event where you don't roll a 4. Okay, suppose that you flip a coin. If A is the event where you get tails, then the complement of A would be you don't get tails, and so you'd have to get heads. By the way, with coins in this class, you can assume that they always come out either heads or tails, and take the probability of getting a coin landing on its edge to be 0. Okay. Okay, so we talked about unusual events back when we were looking at the empirical rule before. Related to that is the idea of a significantly high or significantly low number of successes. Okay, so this part is using probabilities to determine whether results are significantly high or significantly low. Okay, so we'll take high first. So this is kind of wordy, and don't be surprised if you have to read this several times to really get it. But you'll notice that the text here is kind of parallel, and what's different is that they trade high for low, and but a lot of the wording is very similar. So just read through this very carefully. A significantly high number of successes, if we have X successes among N trials, N is the number of trials. When we say trials, that's how many times we do the experiment, how many times we toss the coin or roll the die or whatever. That's a trial. The successes, let's say that we're just to make this concrete, okay? Let's say that our event that we're interested in is getting a 2, okay, when rolling a die. Okay. All right, so if we roll the die, we should expect to get a 2, like about 1 out of every 6 times. Of course, if we only roll the die 6 times, it's conceivable that we could get a couple of 2s or maybe none. But if we roll the die like 600 times, I think we should expect to get around 100 2s, because it should come up 1/6 of the time, approximately. Okay, according to the law of large numbers, it should get closer and closer to 1/6 the more we do it. Okay. So a significantly high number of successes, X successes among N trials, is significantly high number of successes if the probability of getting X or more is unlikely with a probability of 0.05 or less. That is, X is significantly high number of successes if the probability of getting X or more is less than 0.05. Okay, so let's try to make that concrete with our example. And let's say that we roll our die 600 times. Okay, so as you know, we'd get a 2, probably around 100 times. We should get about 100 2s or thereabouts. Okay, if we had 105, that could happen. There's a probability associated with it. We don't know how to count that yet, but there's a probability associated with it. How about if we roll our die 600 times and we got like 300 2s? Okay, that's kind of unlikely, right? That's like a lot of 2s. Okay, there's a probability associated with that. Okay, what they're saying here is if the probability of getting that high number is less than 0.05, then we're going to call that significant. If you roll a die 600 times and you get 112 2s, okay, that's no big deal. That can happen. The probability is going to be higher than 0.05. But if you rolled a die 600 times and got like 250 2s, that's like a lot of 2s. That's pretty unlikely. Probability is less than 0.05. Okay, so that would be significantly high. How we actually calculate these probabilities we'll do later. Okay, what you want to focus on now is this idea of significantly high or significantly low. Significantly high is the probability of getting whatever you got, is that probability less than 0.05? If it is, that's significant. Is it more than 0.05, the probability, then it's not significant. Okay, significantly low is just on the other side. Okay, if we get X successes among N trials, it's low if the probability of getting X or fewer successes is 0.05 or less. So this is just kind of the flip side, so to speak, of this one. So let's say we roll our die 600 times and we get, we should expect 100 2s, but if we get 97 2s, that's no big deal. I wouldn't be too shocked. Okay, but let's say we only got 55 2s. Okay, now that seems weird. Okay, assuming the die is fair, which we're assuming in this class. Okay, so getting 55 2s, that's going to probably have a pretty low probability. If the probability is lower than 0.05, we're going to call that significantly low. Okay, so make sure to read through these two paragraphs, make sure to see how the two statements differ and how they're the same. Okay, and we'll see about how you actually calculate all this stuff later on. I think I got everything here. Yeah. All right, so we're getting there. All right, so a little more. Let's say that you roll a die. We want to know the probability of getting a 4. Okay, as you know, our sample space here is the numbers 1 through 6. There's 6 possibilities, out of which one of them is a 4. So the probability that you get a 4 is 1/6. Okay, what is the probability that you get a number that is less than 7? Well, there are 6 possibilities. How many of those numbers are less than 7? They're all less than 7, right? So 6 out of 6, or 100% chance of getting a number that is less than 7. What is the probability of getting a number less than 1? Okay, how many of these green numbers up here are less than 1? None of them are. So the probability is 0 out of 6, or 0. Okay, as you can tell, something that has to happen, getting a number less than 7, that has to happen. Okay, getting a number less than 1, that never will happen. It turns out that all probabilities lie along that scale between 0 and 1. All probabilities do. So probabilities towards the 0 end are less likely. Probabilities towards the 1 end are more likely. Okay, a probability of 1, that will happen. Okay, something with probability of 0 will not happen. Okay, So that's true, and it's kind of interesting just in a mathematical sense, but it also is helpful in a practical sense for you as a student. When you are doing work for this class, calculating probabilities of something anytime between now and the end of the course, you had better get an answer that's between 0 and 1. If I asked you to calculate the probability of getting like 55 twos out of 600 tosses, you'd better get a number between 0 and 1. It's always disappointing when I see students calculating probabilities and they'll tell me that the probability of rolling a 6 is like 1.3. Okay, probability will never come out higher than 1. Okay, so you can let that be a lesson to you when you're doing your quizzes or taking tests. If it's a probability, it's going to be between 0 and 1. Okay, all of our probabilities obviously are between 0 and 1. There's more than one way of expressing chance. The other way, aside from probabilities, are to express chances using odds. And so that's next. So let's say that you flip 2 coins. Our sample space is to get heads and heads, heads and tails, tails and heads, and tails and tails. Those are our 4 possibilities. If you like, let's make a tree diagram for it. Let's say that you're tossing a penny and a nickel. Just to keep it concrete, the penny could come out either heads or tails. The nickel could come out either heads or tails. Okay, so there's 4 possibilities there, where you've gotten heads on both the penny and nickel, or tails on both the penny and the nickel. 4 possibilities. Okay, let's say that we're interested in the probability of getting both tails. Okay, there's a total of 4 possibilities, out of which 1 has both tails. So when you toss the 2 coins, there's a 1/4 chance of getting both tails. That's probability. A second way of looking at chance is in terms of odds, and how odds work is instead of expressing a part to a whole, the comparison is done a part to a part. So in other words, if you're interested in getting both heads or both tails here, there's one way to get both tails and 3 ways where you don't. So this is the odds of getting both tails. So the big difference between probability and odds is with probability, you're comparing a part to a whole. With odds, you're comparing a part to a part. Okay, here, there's 1 double tail outcome out of 4 possibilities. There's 1 double tail outcome, and 3 where it's not. Okay, that's the odds way of looking at it. This is odds of getting both tails. You'll also see this set as odds in favor. Odds in favor of both tails. If you change your perspective, you could say the odds against both tails. Maybe you don't want both tails. Odds against both tails. That is the same probability relationship, but just looked at from a different point of view. So that would be a 3 to 1 odds. There are 3 ways to not get tails for every 1 way you do get the double tails. Okay, more examples. Suppose that for this you roll a die. E is the event you're rolling a 3, and F is the event where you roll a 2 or a 4. Okay, let's get the probability of E. Okay, there are 6 possible outcomes. You rolling a 3, there's a 1/6 chance of that happening. Okay, the odds of you getting an E. Okay, there's 1, 2, 3, 4, 5, 6 for your possibilities. E is the event you rolling a 3. There's 1 way for that to happen and 5 ways you don't. So the odds are 1 to 5. By the way, in addition to seeing this written with a colon, sometimes people will write the word 2 in there instead of the colon. Either way is okay. All right, the probability of F, you getting a 2 or a 4, we wanted the probability out of 6. There are 2 outcomes that are 2 or 4. In this class, you always want to simplify fractions and ratios. So simplify that 2/6 to 1/3. Okay, don't go crazy turning it into a decimal and put down 0.3 because 0.3 is not 1/3. Okay, 0.3 repeating would be 1/3. So let's just leave that as 1/3. Okay, the probability of F complement. Okay, that's the probability of not getting F. Okay, well, F was a 2 or 4. There's 6 possible outcomes. How many are not 2 or 4? There are 4 that are not 2 or 4. That's 2/3, which makes sense. The probability of getting F was 1/3. The probability you don't get F then should be 2/3. Okay, last one, the odds against F happening. Okay, so F, there's 2 ways that F can occur. The odds against F, that means you're like against F, you're on the opposite side. So there's 4 ways that you can not have F occur for every 2 ways that F does occur. That leads to the ratio 4:2. We're going to simplify that ratio down to 2:1. There are 2:1 odds against F. Right, so that takes care of most of this section. What we're going to do next is look at some more examples. So these ones are taken from our textbook. Here it says, in the directions, it says, express the indicated degree of likelihood, that's the chance, as a probability value between 0 and 1. So let's try the ones that are yellow highlighted. When arriving at the traffic light closest to the author's home, there's a 25% chance the light will be red. So that's 25 out of 100, 25%. And of course, we're going to simplify that to 1/4. If you want to make that 0.25, that's okay. It's equal to 1/4. Okay, if you make a random guess for the answer to a true-false test question, there is a 50-50 chance of being correct. There's 1 correct answer out of 2 possibilities. So you have a 1/2 chance of that happening. When they say 50-50 chance, they're referring kind of to the odds. For every 1 correct answer, there's 1 wrong answer. Remember that probability refers or compares a part to a whole, where odds compares a part to a part. Okay, for the SAT test, when guessing the answer to a multiple choice question, the chance of guessing correctly is 1 in 5. Okay, let's go ahead and put down the odds for that as well. For every 1 correct answer, there are 4 incorrect answers. So the odds of getting the right answer are 1 to 4. The probability of getting the correct answer is 1 in 5. Okay, it's impossible to pass a statistics test without studying, so that's going to be a probability of 0. Okay, let's try a couple more. Here it says Microsort's XSort gender selection technique is designed to increase the likelihood that a baby will be a girl. In updated results of the XSort technique, 945 births had 879 girls and 66 boys. And then they give a source. Based on these results, what is the probability of a girl being born to a couple using this method? Does it appear that the technique is effective in increasing the likelihood that the baby will be a girl? So all we're doing here is just to write the probability, right? So what is the probability? Okay. So there were 945 births, and out of that there were 879 girls. Okay, and so that's it. So that's the probability. To me, it looks like, yes, it's effective. Otherwise, we would expect about half of 945, and that's like 472. So we had way more girls. So it does look effective. Okay. We could do odds. Why not? So let's do odds. The odds of getting a girl, just for practice. Okay, that would be 879 girls to 66 boys. There again, we're comparing a part to a part rather than a part to a whole. Okay, next one. In a poll, respondents were asked if it should be legal or illegal to send a text message while driving. 8 said that it should be legal. and 804 illegal. Okay, what is the probability of randomly selecting someone who believes that it should be legal to text while driving? Okay, so the probability of picking someone legal, that would be 8. And here you want to be careful. It's not 8 out of 804. How many total people were surveyed? There were 8 legal and 804 illegal who said it was illegal, and so that total is 812. Okay, so that's 8 out of 812, so we can divide that by 4 at least. So that's 2 out of 203. Okay, so is it unlikely to randomly select someone with that belief? I would say, yeah. There's only a little under a 1% chance of that occurring. All right. So we can change that to a decimal so you see that easier. So that's about 1.9%. Okay. Okay, a couple more examples. Okay, suppose that E is an event and the probability of E occurring is 5/8. We want to find the odds in favor of E and the odds against. So you should pause the video here and try this yourself and see what you get. And then we'll go from there. Okay, so one way to do this, you might want to make a picture, especially if you're just starting out. The probability is 5/8, so the denominator is 8. So I'll make a little picture of a box and divide it up into 8 pieces. And so it says the probability of getting E is 5 out of 8. So there are 5 E outcomes and then 3 that are not. Okay, so you can picture like 8 cards, and 5 of them have an E printed on them and 3 are blank. If you pick out 1 card at random, you got a 5/8 chance of getting an E. Okay, we want to find the odds in favor of getting an E. So that means for every 5 E's, there are 3 not E's. The odds against them, you just turn the ratio around and make 3 to 5. For every 3 ways you don't get an E, 5 ways you do. Okay, last example. Okay, in a sample of 50 people, 21 had type O blood, 22 had type A, 5 had B, and 2 had AB blood. We want to find these probabilities. So there were a total of 50 people. We wanted to know the probability that a person has type O blood. There are 21 people out of the 50 who had type O blood. So we'll leave it at that. A person has A or B. 22 had A. 5 had B. So that's 27 have A or B. That's 27 out of 50. A person has neither type A nor B blood. That would be everybody else out of the 50, right? That is kind of the complement of the previous event. So that's going to be 23 out of 50. And then lastly, a person does not have type AB blood. There were 2 that were type AB out of the 50. So if they don't have type AB, that would be the other 48 people out of 50. All right, so that takes us finally to the end of this section. Make sure that you read through the section if you haven't already, and read through the notes. And let me know if you have any questions, and have a great day.